Welcome. This video is going to look at the practice problems found at the end of Chapter 5. So instead of 5.2 problems here, I should really have written just Chapter 5 practice problems. 1 through 8 from 191 to 193, and these are the multiple choice ones. So number 1 gives you some information and says a pure aluminum block with a mass of 10 grams is heated. So its initial temperature is 20, final temperature is 50, or a temperature change of 30. They give you the specific heat, and it's 8.99 times 10 to the minus 1, which is correct scientific notation, but you can just think of this as 0.899. And it's given as joules per gram per Kelvin degree, but there's no need to change these temperatures to Kelvin, because when I subtract them and get my delta T of 30 degrees Celsius is the same amount of energy as 30 Kelvin. So do not let this Kelvin mess you up. So the only thing slightly tricky is when they ask for the expression that gives the heat energy, they want it in kilojoules. So I need MCAT divided by 1,000 to express this in kilojoules. So that would be 10 times the 0.899, or the 8.99 times 10 to the minus 1 as they wrote it, times 30 divided by 1,000. And that corresponds to their choice of, appears to be, excuse me, D. In question number 2, they want to know which of these processes has an exothermic delta H, or a negative enthalpy change, because negative enthalpy is the same as exothermic. So if I look at process 1, I've got methanol combining with combustion and giving me CO2 and H2O. So combustion is always exothermic. So 1 is definitely an exothermic or negative enthalpy. Number 2, I've got an acid and a base. I recognize the H and the OH, plus I'm getting a salt and water. So this is a neutralization, and neutralization is also always exothermic. Number 3 is just a physical process of changing a gas to a liquid, just a phase change. But when a gas goes to a liquid, you need to slow down the particles and lose energy. So this is going to be an exothermic process as well, as you get rid of the excess energy. So for number 2, all 3 of them are exothermic, so D would be your best choice. Number 3 is a tough question, because when you look at it, you've got beaker A and beaker B, and each one has the same size of magnesium being put in, and beaker A has HCl that's 100 cc's and 1 molar. So when I multiply my 0.1 times 1 molar, that means I have 0.1 moles of HCl. And my magnesium, my beaker B, has 200 cc's, or 0.2, but it's only 0.5, so that's also 0.1 mole. So what's tricky about this is that if I plug it into MCAT, the delta H is going to come out being the same. But what you need to realize is when I do delta H for A, I've got 100 grams times the 4.18 times whatever my temperature change is. And with beaker B, now I've got 200 times 4.18 times delta T. So if this number has to be the same, if these two have to equal each other, delta T for A is going to have to be less than delta T for B is going to have to be less than it is for A. A is going to have twice as much for these to equal each other. Because, and another way to think of it is B, is even though it's going to have the same heat energy, it's got more mass to distribute that heat energy in. So the temperature change is going to be less for B and greater for A. So that corresponds with A, which said the maximum temperature in A will be higher than in B. But if you were thinking, but the heat change should be the same, you are correct. The heat change will be the same, but the temperature change will not be. Number 4 is an example of Hess's law, and it's pretty straightforward. When I look at my first reaction, I see that I have CuO on the product side, which is what I want. And initially, it looks like I need to double it, except you have to look carefully because my second equation also has CuO, but it also has the Cu that I'm going to need. So this one I'm going to have to flip. So it's going to become a negative 11. And when I flip it, that means one of my CuOs is going to cancel out. My Cu2O is going to cancel out. So I actually just leave letter A. So leaving A and flipping B means I'm going to have negative 144 plus a negative 11. So that corresponds with answer C. Number 5 wants to know which of these reactions represent an energy equal to an HCl bond enthalpy, or breaking one HCl bond. Well, if I look on the left side, on the reactant side, A, B, and C all break one HCl bond. D is going to be a problem because it's breaking two HCl bonds. So if it formed an HCl bond on the other side, it would be okay, but that's not the case. So I can pretty quickly eliminate D. The other thing to check and see, are the reactants and products all gases? And they are for all 4 equations. So then the other thing is to look at the reactant side. If the products are at the product side, if the reactant side is breaking one HCl, then I need to have no energy being expended or released on the product side. In the first one, I'm ionizing hydrogen to H+, and that's going to require energy, so this is not going to be a net value equal to HCl. In B, H plus Cl, there's no new bonds there, there's no ionization, there's no phase change, so this seems to be our best answer. Whereas C, I am forming a new H2 and Cl2, and even though I'm only taking half those values, that's still going to not give me a net HCl value. It's going to distract or subtract from that value. So B would be my best choice. Number 6 is another example of Hess's law, and this one's kind of messy because we've got 3 equations, so it's a little bit harder to keep track of things, and equation 2 is a little bit harder to find what it's doing. So let's just start looking at this. I've got equation 1, I've got CH4, which is my reactant. I've got some O2, which is not enough, but I see I have O2 in every equation. I have HCHO, which I don't need. I have H2O, which I will need. So it appears to be going the right direction, but since I don't see CH4 anywhere else, I'm going to have to double this to come up with 2 CH4s. The second equation, the HCHO doesn't show up in my final equation. The O2 does, so that might be helpful. And then the HCOOH doesn't show up in my final, so it kind of looks like equation 2 was just put in there as a distractor, or what we call a red herring. But if I go on to equation 3, I will see a purpose for equation 2. So equation 3, I have 2 HCOOH, which isn't part of my final equation. O2 is part of the final, and it's on the correct side. COOH2 is part of the final, and it's on the correct side. And H2O is part of the final. So equation 3 seems to help me out and seems to be in the correct amounts for the things that show up in the product. At least the COOH2 is in the correct amount, and that's the only place it appears. So I'm going to assume I just leave equation 3 as is. In order to get all this other stuff to cancel out, though, I'm going to need equation 2. I'm going to need it to cancel the HCOOH in equation 3, and I'm going to need it to cancel the HCHO in equation 1. And in equation 1, because I've doubled it, I'm actually going to need it to cancel out 2 HCHO, and in equation 3, I need it to cancel out 2 HCOOH. So I'm going to double equation 2 as well, and when I double a half, that becomes 1, and double it. So when I add this equation up now, as I add down, I have 2 CH4 carries down, 2 HCHO cancels out from up here. The 2 HCOOH cancel here. The O2s now add up as we go down to 3.5 total. On the other side, the 2H2O comes down, picks up 1 more to be 3, and the COOH2 comes down. So apparently I've treated my equations correctly, and it should be 2x plus 2y plus z, which corresponds to letter C. Number 7 wants to know which one represents a bond enthalpy of a single carbon-chlorine bond in CCl4. So first thing I want to look for is if the reactants and products are all gases, because bond enthalpy is always referring to everything in its gaseous state. So C and D I can eliminate right away because they have liquids and solids in there. So it's either A or B. And A and B both look pretty good because CCl4 making Cl and 4Cl4, that breaks all the bonds, so that seems like what we want, but this is actually 4Cl bonds, CCl bonds that got broken. So unless I divided this delta H by 4, that's 4 times more than I want. So instead, in equation B, CCl4, if one chlorine breaks off and leaves behind CCl3, this is representing just one carbon-chlorine bond, so B is my better choice. A would be okay if I had the option to divide by 4. But once again, IB gives you a really good wrong answer for letter A. Number 8 wants to know what would be the energy liberated when you burned 1 mole, when you combusted 1 mole of carbon monoxide. Well, according to the equation, 2 moles of carbon monoxide gives me negative 564 kilojoules. So if I wanted just 1 mole, if it's negative 564 kilojoules per 2 moles, I can just divide by that and I will have my kilojoules per mole, which should be negative 282, or answer B.